continuing the theme of measurement, analysis, and simulation that we have going on today. Our next presenter is also a heavyweight in this industry. I'm a fan of his work. In the panel discussion, you heard him talk about modeling the space station, which I think is a fun topic. I grew up in Houston, Texas. I think I mentioned that yesterday, and was always a fan of the space program. And anything space station, spaceship, I'm interested, and I suspect many of you are as well. So our next presenter, really known for two things, aside from simulating the space station, would be power integrity and pizza. As a matter of fact, I will be going home this evening and preparing his pizza dough recipe so that I can make his apparently world famous pizza dough recipe that now I know requires a 3-day rise. I didn't know that before I met Steve Sandler. And with that, let me introduce Steve Sandler. Thank you so much.
Steve Sandler has been involved with power system engineering for more than 40 years. Steve is the founder of Picotest.com, a company specializing in power integrity solutions, including measurement products, services, and training. He frequently lectures and leads workshops internationally on the topics of power, PDN, and distributed systems, and is a Keysight certified expert for EDA software. Steve frequently writes articles and books related to power supply and PDN performance, and his latest book, Power Integrity Using ADS, was published by Faraday Press in 2019. Steve founded AEI Systems, a well-established leader in worst-case circuit analysis and troubleshooting of high-reliability systems. Please welcome Steve Sandler.
Hi, I'm Steve Sandler, and I hope you're enjoying the Altium conference. Today I'm excited to talk about simulation as an essential tool. There's a lot of reasons that we do simulations, and this is just 3 of them. So one reason is that the data that we get from manufacturers is often inconclusive, and even more often it's probably just bad data. Another is that reference designs and design recommendations aren't normally well vetted, and so we can get into a lot of trouble using a design that hasn't been well validated and correlated. And so we do that through simulation. And also because we're inherently biased, and I often say that numbers don't lie, and so we're using simulation to provide the numbers that give us facts rather than our own biased interpretations. There's a lot of other reasons that we simulate too. One is to compare components, topologies, or technologies. If you're asking the question, should I be using gallium nitride or silicon carbide? Or hey, Texas Instrument came out with a new pulse width modulator. Should I be using that one? The best way to determine things like that is through simulations. We use it to optimize our design. So, once we have a design architected, we can generally optimize it through simulation if the models are good. We use it to find problems before they're committed to hardware. Problems can get really expensive, and when we use nasty words like recall, that sounds very expensive, and we don't really want that to happen. And so it's best for us to find issues in our designs before they get committed. Of course, a lot of my work is design for aerospace and defense, and once you've launched it, it's launched, and we do hope that the missiles go where they're supposed to go, and so we want to make sure that everything's right before it gets released. Simulation is a valuable tool for doing that. We also use simulation to evaluate things that we couldn't evaluate using other simple methods, either because the results are destructive or because, for example, we can't acquire a component that has worst case minimum HFE or something that's been exposed to radiation to certain levels. And so we do that through simulation. We can use simulation to troubleshoot problems and to provide direction for redesigns, and I'm going to show you some examples of that during this talk today. We also use it to define things like the acceptance test procedure limits. You'll very often see in a data sheet where it says guaranteed but not tested. And that often means that they're guaranteeing it by the corner simulations that they did in their design process. And so we use simulation for all of these different reasons. Now honestly, I'm pretty old, but it didn't really start at the very beginning with SPICE. SPICE was written by Larry Nagel back in 1969, and I didn't really start simulating until the mid-80s roughly. Back in the 1970s, my first project was the space shuttle in 1979. And back in those days, I was still using a slide rule while I was going to college to finish my degree. And in fact, I failed a physics test because the batteries in my calculator went dead. And so after that, I started using both the calculator and the slide rule, and I would use the slide rule to validate my calculator. Not sure why I bothered. In the mid-1980s, I was working for a company that finally started to get computers, and we simulated in a program called ECAP. Back then, it was quite a bit simpler and less sophisticated than today. We didn't have schematic generators, so it was all netlist driven, and we used 3D matrix printers to create the line drawings of the simulation output. So it wasn't really very sophisticated. But I got involved with SPICE around 1990 in a big way with Intusoft. So today my partner is Charles Heimowitz, and back in those days he was one of the founders and also vice president of Intusoft. And they made a pretty decent SPICE simulator. In fact, back in the day, it was probably one of the best. In 1995, I started a company called Analytical Engineering. Later it became renamed as AEI Systems, but Analytical Engineering started as a company that was solely dedicated to creating models, doing simulations, and worst case analysis, mostly for large satellite systems. And today it's more high reliability systems, and that's inclusive of things outside of satellites. But back in those days, it was pretty much all satellites. And I couldn't afford a simulator, so I worked out an arrangement with Intusoft. They provided me with the simulator, and I wrote the power library for Intusoft SPICE, which is now available from EMA for PSPICE. And I wrote my first SPICE book back in 1995. It was published in 1996. It's been released a few times since then, most recently in 2018. I also wrote something called the SPICE Circuit Handbook together with Charles. And in the SPICE Circuit Handbook, we created a selection of circuits, we built them, we tested them, and we compared simulation results from various simulators, including simulation times, to see how it is that they compared and how accurate they were. In a large part, this was to dispel the whole garbage in, garbage out. You can't do much with SPICE thinking that was pervasive through the middle 2000s, I guess. Then in 2014, I wrote my book, Power Integrity, which was really sparked by the fact that I was really struggling with the fact that most measurements that I received were bad data, even when they came from the manufacturer. And so I started making models only from my own measurements. And in 2014, I published my book, which was mostly about making measurements. And then in 2019, I published PI Simulation with ADS. So used properly, SPICE can really do a lot of things for us. And here are a few examples. On the left side of this screen, you can see two plots. One is a simulation. The one in the upper left is a simulation, and the one in the lower right is a measurement. The customer is having trouble with a high voltage power supply, and they wanted to see if we could figure out why. So we constructed a model, and you can see the burst oscillation modes at low frequency that occur both in the simulation and in the measurement, and that allowed us to troubleshoot the problem. In the middle column, there are two different plots. The upper one is a gate drive to a MOSFET. When we look at gate drive and MOSFETs, we're particularly interested in two things. One is a very small plateau during the rising edge. That's called the Miller effect, and that controls the drain switching time. And also we want to make sure the voltages are nice and square with no overshoot, because gates can be pretty sensitive to overvoltage, particularly in gallium nitride and silicon carbide. You probably can't see it well in this picture, but that is an overlay of both the simulation and the measurement. So that's a pretty good model. And in the middle on the bottom, we have a static inverter, and I've always been fascinated with creating sine waves for all different purposes. In the SPICE circuit handbook, I have quite a few circuits that I used to generate sine waves, either for lamps or for small, low-power battery backup systems. And I'm always playing with different ways to do that. This architecture is called harmonic neutralization. And so you can see in the bottom of that plot, in the center bottom graph, it looks like a square wave, but with a bunch of notches cut out of it. And those notches each represent some Fourier harmonic. And if we create the notches at exactly the right size and put them in the right place, then we remove many of the harmonics from the square wave, and that makes it really easy to filter. And again, you might not be able to see it well, but that is the simulation and the measurement on top of each other. So another good model. In the upper right-hand screen, we have a Bode plot, and again, that is a simulation and a measurement, and we use that to verify the stability of a power supply. And in the bottom right, this is probably one of the most common measurements that we make, and it's just a measurement of a small decoupling capacitor. And that again is a simulation and a model on top of each other. So another really good model. So the point is that we can create really good results if we can create really good models. And without really good models, you get the garbage in, garbage out syndrome, and that doesn't really go well. We get to a large scale, like the International Space Station or the Large Hadron Collider. I've been really fortunate in my career to work on both of these. We create these monstrous systems that are very intricate, containing thousands and thousands of circuits built by thousands of engineers in a variety of countries, and somehow when we stick them all together, they work, at least most of the time. The reason that they work is because we can create boundaries in SPICE that allow us to validate the interface between different circuits. And so if we can validate the impedance and simulation of a circuit on the loading side, and we can validate the impedance on a sourcing side, then we can simulate the fact that those two will be compatible. We do the same thing when we get to something as big as the Large Hadron Collider. This is actually just a forward calorimeter. I love to tell stories. It was one of my favorite projects, but for a lot of reasons. And one of the reasons is that I was working on the Large Hadron Collider for Brookhaven National Labs. And my younger daughter is a physicist who happened to be working on this calorimeter at U of A. And for one day, I got to work with my own daughter, which was really a blast. But anyway, even something as big as the Large Hadron Collider, we're really relying very heavily on SPICE to get the results that we need. And I'm going to show you why that is. And so the reason I was working on the Large Hadron Collider, as you may or may not remember, but when they first turned on this calorimeter, it didn't actually work. And nobody was really sure why, so I was called in as a consultant to try to figure it out. And we knew that it was the power supply that wasn't functioning, and so we looked at the power supply, we created models, and in fact you can see one of the reasons that it didn't start here in the measurement plots on the right. And those are plots of the power supply during turn on, and you can see that in some cases we built a rogue wave and the power supply didn't turn on. In this case, we're building the simulation model and we're following the Rule 9 Eric Bargaden likes to tout, and we have the same rule. We don't go into the lab until we know what it is that we're looking to find, and in this case, we came up with a bunch of scenarios using SPICE to see if we could figure out which ones we could capture in the lab that would be reasons that this accelerator power supply wouldn't start. And we did ultimately figure it out, and we found 13 different reasons why this power supply wouldn't start. Working with Brookhaven National Labs, we created a retrofit program, and we went into the lab, and in the lab they were able to validate 12 of the 13 findings that I had. And so we retrofitted those 12. After we finished, they got a call from the physicists at Brookhaven National Lab saying, "Steve, guess what? We just got a picture of number 13. And so it was back to the drawing board. We fixed the 13th failure, and ultimately they were able to start the Large Hadron Collider, which has been very successful. After that, I gave a paper in 2008 at a particle accelerator conference. It was kind of fun. It was a great chance for me to get to Italy. The conference was in Genoa, and I had this picture of the forward calorimeter on my poster. And one of the engineers or scientists came up to me while I was at the conference. You might be able to see him. He's a little tiny figure right here in the front of the calorimeter. And he introduced himself to me, and he said, "That's me." And I said, "Oh, wow, that's really cool. Very nice to meet you." And he was standing with another older gentleman, and he introduced me to the older gentleman. He said, this friend of mine, he designed all of these electromagnetics. In fact, he designed everything you see in this picture. And he was standing right in front of me, but unfortunately, they cropped him out. And so it's kind of funny the way things like that happen. And it's just a funny story. But I feel bad for the guy that designed all of that. And in that very famous picture, he doesn't appear. So we have to have good models, and you have to start out with the assumption that vendor models are suspect. I won't say that they're bad, but they should be suspected of being bad. And that's not always the vendor's fault. When the vendor creates a model, many times they are bad. But sometimes they're very well documented, and they provide lists of what is and what isn't included, and what's accurate and what's not accurate, and those are delivered in a report along with the model. When it gets to the simulation company, they integrate that model into a large database or library of all of these models, and all of that documentation is gone. And so now you have this model, you just have no idea how good it is. But the majority of them are not well vetted. So I have a very simple rule, and that is that I won't use a model that I didn't create or didn't, at the very least, vet. We are, firm believers in the fact that there's garbage in, garbage out, but we also believe that there's no such thing as a perfect model. So we're always making compromises, and I love stories. I'm going to tell you another story. When I was working on the International Space Station, we had a custom MOSFET made by Harris back in that day, and they referred to it as the SuperFET. We waited about 3 years and spent almost $200,000 to get an accurate model of that SuperFET, and we ran it exactly one time. It took a couple of days to run, and it gave us a very nice picture of gate drive, but we decided that it was too slow to actually be useful. And so one of the compromises that we're trying to make is that for it to be useful, it also has to run fast. And so we're always trading off accuracy and simulation speed and what to simulate and what not to. There are many incorrect beliefs. One is that we're creating the simulation in order to verify the measurement. And that's not always true, but it can be. We are always interested in validating the model, and that means that we do have to have a model and measurement that agree. And often we want to make sure that we can do that in many different operating conditions. Otherwise, we could just draw a picture, but the picture won't have the same sensitivities as the actual circuit. And in other cases, like one I showed you earlier, we think that there's an issue. We have a simulation of what we think the issue is, and now we're going to go see if we can find that in the lab as part of our measurements. And simulation provides us a good way for us to go explore those kinds of things. Now, obviously, when I'm working on projects that are as big as the space station or the Large Hadron Collider, and they're both valued at about the same value at about $16 billion. Here I am sitting in my living room in Chandler doing the simulation and modeling of the space station. So I'm sitting on one side of the table, and there's NASA, Space Systems Loral, and Rocketdyne on the other side of the table. And my job is to tell them that their baby's ugly and find all of the issues before it is that they go ahead and launch it. And so if you're going to tell NASA their baby's ugly, my first rule would be, you better be right. Here's one of those cases, and it takes a lot of simulation and a lot of experience to get to the point where we have this confidence, but it is the goal. This is the first system-level simulation I did of the space station back in the later 1990s. And so when the space station goes through a solar eclipse, it switches the main power from the solar arrays that capture the light from the sun to running from batteries while it's in the dark, and obviously it has to go through a transition between those two. And so here is the battery and solar array power bus in this upper trace. On the left side, we're operating from solar power, and the voltage is slightly higher than it is when we're operating from battery power over here. And here's the transition region where we go from solar power to battery power. The green line that runs right through that transient is the master reset level. And what that means is that anytime the bus crosses that threshold, every computer on the space station resets. And of course, that green line goes right through the transient, which would mean every time the space station goes through a solar eclipse, it's going to reset all of the computers. Of course, it could be a case of garbage in, garbage out. That's a possibility. And on the other hand, at 17,500 miles an hour, the space station goes through a solar eclipse about every 90 minutes. This middle trace is the load current, and we actually stepped up the load current in order to get the power bus to switch from solar power to battery power. And here's the current, and here's the solar arrays, and here's the batteries. You can also see the very large battery overcurrent. Of course, we didn't have any hardware yet. All we had were simulations. It was almost 18 months before this picture crossed my desk. That was the test they got data for right after they built the hardware, and it really did come with that post-it note. And what I said at the time is, the good news is, yes, I can fix it. And the bad news, at least for you, is that my rates have gone up a lot in 18 months. But you can see that there's a lot of similarities between the simulation and the measurement. I wouldn't call them identical, but I'd call them very damn close. And so part of the reason that we're working so hard at our modeling and simulation is because I often tell my customers that at some point, and it's going to be different for different projects and it's going to be different for different engineers, but at some point, you're going to have no choice but to trust the simulator, and when you do, you really need it to be right. And it takes a lot of experience and a lot of work and a lot of modeling effort and a lot of measurement accuracy in order to make that happen. But that's what we're after. We're after making sure that these models are nearly perfect. We start with basics like capacitors. So if you've modeled a capacitor, you may have seen that it's not as easy as it looks. Back in 1990, I wrote a ladder model, which is a bunch of capacitor, resistor, and inductor elements that represent an electrolytic capacitor. And I wrote it back then for aluminum electrolytic and CLR79 wet tantalum capacitors. I don't use that topology anymore because it was very hard to manually tune. And it wasn't all that accurate. It took a lot of fiddling to get it to be pretty accurate. Some manufacturers still use my ladder model. Now we use a little bit more simplified topology, but it's much easier to tune. And so here again, you can see there's an overlay of the measurement and the simulation. These are actually documented in a video that I did for Keysight on the How to Power Integrity video series, and this one's on measuring and modeling capacitors and inductors. One of the odd things about tantalum capacitors and also aluminum electrolytics is there's a region where it's capacitive, and we can see that right here on the left side of the plot. And then there's kind of a break where the slope changes, and that slope is a frequency dependent, kind of resistive, kind of capacitive region. Then there's a series resonance, and so we have this resonant frequency and resonant ESR, and then it becomes inductive again. And so we need a model that can replicate all of that. And so one of the first things that we learn to model is the capacitor. And that means that typically we're doing things like aluminum electrolytics, and we're also modeling our decoupling ceramics, the decoupling capacitors. One of the things about making these models is when we make the measurement is generally made mounted to a printed circuit board. And how it is that we make the measurement will determine how much of the printed circuit board is seen. But these measurements are only the capacitors, the capacitor plus the printed circuit board, and ultimately those need to get removed. So then we can combine these into larger circuits, and in this larger circuit, this one is actually from a DesignCon 2018 session that I did together with my friend and colleague Heidi Barnes, and she's giving a session here at AltiumLive also. But this was a Xilinx board, and we did a paper together with myself, Heidi Barnes, and Jack Carroll from Keysight. This plot here on the lower right is actually the supply voltage to the MGT transceivers. And this is enabling a transceiver, and here's the voltage transient and the current transient that occur when that power is applied. You can see the voltage droop right here. And unfortunately, that voltage droop is much larger than the 10 millivolts that Xilinx allows. And so part of that DesignCon 2018 paper was to figure out what caused that and how to fix it. And so that takes a little bit more sophisticated model, but this is a state-spaced average power supply model. I wrote this back in about 1990. I published it in my first book in 1995, and it's been consistently published and also updated a few times since then. In 2015, I ported it to ADS to make use of some other features that I'm going to show you in a minute. There's also a slope compensating ramp generator that exists in these power supplies, so we need to model that. There's a feedback amplifier right here, a voltage divider, and of course here's the output capacitors, and here's the MGT transient. What's over here is kind of interesting, but that is a harmonic balance representation that takes the state space output, which is in frequency domain, and converts time domain data from it. And what's really unique about that is that I wrote that back in the mid-2000s when they started doing things like WebBench, where we were simulating over the internet. Remember, I said speed matters. Transient simulations are really, really slow. We needed to find a way that we could do time domain simulations much faster over the internet. And I published a hybrid method back in, I think it was 2008, together with National Semiconductor, that used the information from the state-space model to recreate the results. And here in ADS, I'm doing that using a harmonic balance engine. And so we need to model many things for this, including the capacitors, the inductors. We need to make measurements of the state-space model, so measurements of the power supply to populate the parameters of the feedback amplifier and also the power supply. Anyway, if you're interested, you can email me and I'm happy to share that DesignCon paper with you, but we did ultimately successfully complete the simulation and also correct the deficiency in the power supply. The output looks something like this, and this isn't that particular power supply, but this is one that I publish quite frequently. And here you can see from the state-space model, we're getting the time domain switch waveforms, we're getting the time domain ripple voltage and inductor current. We can see the spectral content if you're interested in designing EMI filters and the like. Here's the output impedance, and that's what's responsible for the dynamic transients from the high-speed stuff. Down here in the bottom right, that's the Bode plot. That confirms the stability of the power supply. Here's the capacitor measurement and simulation, and you can only see one curve, which means they line up really well. We have the error amplifier gain, the power supply rejection ratio, and even the negative resistance. And all of that comes from that one model that runs in less than 1 second. And so that meets the criteria for being fast enough to provide useful information while providing the details that we need to fine-tune, optimize, and troubleshoot our power supply designs. And so that's really what we're after. We also want to make sure that we're creating models and not drawing pictures, and I talk about those words frequently. Back around 1995, I wrote the simulation modeling and worst case analysis class for Motorola University, and I taught that class up until the university closed, and I still continue to teach that for large prime contractors now. But one of the things that I talk about in worst case analysis and modeling is you really need to pay attention to all the little details. And so here's a family of Bode plots, and you can see the gain curves here in this upper window and the phase in the lower window. And there's two things to note about it. One is that the gain curve changes an awful lot with load current, and that's frequently the case with linear regulators, not so much with switching regulators, but linear regulators have this sensitivity. But I want you to focus your eye on is this little tiny wiggle that shows up right here where the arrow is. That's easily overlooked, but that actually tipped us off to the fact that there was an inner loop in this power supply, and that inner feedback loop was unstable and showing up as this little divot. Now that divot could have been noise, except that noise generally doesn't repeat itself so accurately, so it wasn't likely that that was noise. But things like this actually get written off quite frequently by engineers as anomalies, oddities, or other random noise events when they're not. And so you need to be really attuned to those things when you're making measurements. I'm going to show you a couple of other examples of that a little later on in this presentation. But I'll tell you another story because I like stories so much. But in one of these stories, I was working on the International Space Station. We did a simulation of a battery bus. So it was actually the interconnect between a battery and the battery charger discharger unit. And our simulation said that it was oscillating. And of course, the customer didn't believe us and said, you know, SPICE does things like that, garbage in, garbage out. I don't know why SPICE has such a bad rap, or maybe I do. Maybe it's because so many models tend to be on the less than stellar side, and so people have come not to trust them. But I've been doing this a very long time and I'm meticulous about my modeling, so I doubted very much that I could be wrong. But that's not the surprising part. The surprising part was I jumped on a plane to Palo Alto, and I'm sitting in a room with this power supply, and there was 4 kilohertz so loud that my ears hurt. And I asked everybody, what is that noise that we're hearing? And nobody knew. Everybody said, it's always been there. So we got a giant current probe, one of those Tektronix current guns that looks like a pistol. And we put it on the battery cable, and sure enough, 200 amp sine wave, the battery cable was oscillating at about 200 amps at 4 kilohertz. How does that happen? You know, the company that I did this effort for was meticulous about their modeling, and they modeled every single box in this entire satellite. And so they questioned how it is that they possibly could end up with a scenario like this, where they had an unstable battery bus and didn't know it. And there's 2 things that are notable. One thing that's notable is that how come nobody heard this really loud 4 kilohertz noise that was coming out of this box? They should have, but they didn't. The other thing that I want to take away from this is that the interconnects are really important. They didn't model the cable, and the cable made the circuit unstable. And today, that's very often the case in backplanes, connectors, ribbon cables. Those do the same thing as that cable, and so those really need to be included. But I'll tell you another story also about Space Station. When it came to doing the analysis of the stability for the solar array, I had no idea how to do it. It's a very difficult analysis, and I didn't really know anybody but one person in the entire country that knew how to do that analysis. And his name was Dr. Vincent Bello. He was a brilliant, brilliant engineer. And back in the 1970s, he was doing state-space modeling. And quick aside, while he was working on Space Station, he found out he had a heart condition and he was going to die in the next couple of years. And he spent those couple of years attempting to prove that he did the first state-space average model. Probably not how I would have spent my 3 years. But anyway, he spent a long time doing the analysis of the solar array for the space station. And finally, when he was finished, he presented his results to NASA and Space Systems Loral and Rocketdyne, and he said there were 80 unstable regions in the solar array system. And it was interesting because they were all below 1 hertz. They were very low frequency, but there were 80 different unstable regions. And one engineer from the solar group says to another one, do you think that's the clicking that we hear? And so again, this is this inherent bias that I talked about in the very first slide. We tend to not like, or we tend to disregard things that are working against us. We don't like what it means, we didn't see it. And so for that reason, one of the things that I often recommend is that engineers should not be doing simulation, modeling, and analysis of their own circuits because they have a bias in the outcome. That should almost always be done independently. But back in the space station days, also, if you could read the reports, and I think there were a total of almost 300,000 pages of reports that I generated for the space station, every single one of them had a little note that said, and this analysis does not include printed circuit board effects. Today, I would say don't even bother because it's all about printed circuit board effects. This is a simulation, and the measurement actually did confirm this relatively well, but I'm not allowed to to show the actual measurement data. But this is a gallium nitride switch, and this is the ground bounce of that switch, and you might not be able to see the axis real well, but that's a little bit over 2 volts of ground bounce. The gallium nitride switch is allowed a maximum of 5 volts, and the enhancement region is at about 2.5 volts. So there's very little wiggle room between fully enhanced and over voltaged, so we can't really tolerate things like this ground bounce, and that becomes a really major element in the circuit. In fact, that is the single largest signal other than the gate drive pulse itself. And so we really need to be aware of where it is that printed circuit board impacts will get in the way. And I think that there's a tendency to believe that the printed circuit board effects will get in the way at much higher frequencies and not in the lower frequencies. But I can tell you that we very frequently see printed circuit board phenomena in hundreds of kilohertz. You don't really need to get all that high in frequency in order to be able to see it. Sometimes I like to say that less is more. If you were to look at the power library that I wrote for iSpice and the one that's currently sold by EMA for PSpice, you'd notice that there are different levels of models. For example, if I wrote a pulse width modulator model, there are pieces of it. It's a modular system. I can take just the gate drive section and run just the driver without running the whole pulse width modulator. And the same thing, I can do that with the feedback amplifier and the oscillator. And so, one of the things that I teach engineers is to get the fastest speed, we want the less baggage. And having excess baggage that's going to simulate and not create an impact on the results takes time and money in a couple of ways. One is that it's something else that needs to be validated, and it's something that we end up often troubleshooting because the simulation won't work or because we run into convergence problems. If any of you have run into SPICE, I'm sure you've never seen a convergence problem, but, well, I'm lying. Of course you have. There's nothing worse than getting to the 500th simulation in a Monte Carlo and having it crash on you. So we don't want to carry extra baggage. We want to simulate the absolute minimum necessary. And if we're simulating something like the gate drive of a pulse width modulator, we can do that very accurately. But the computational time is exorbitant, just like in the case that I mentioned about the space station gate drive simulations. And so there are cases we might need to run that. And if we want to run that accurate gate drive model, then we would probably just take just that gate drive piece and put it together with the MOSFET and run only that without running anything else along with it. And if we're running it as part of a system, the details of the gate drive become much less important. So there are also other versions of the model that have logic gate outputs, and those will simulate much faster with much better convergence. They just won't show all of the intricate details. And so when we're simulating things like stability, there's no reason for me to be including startup and overcurrent and all the other ancillary functions that are included in that model. I want to pare down this model to the minimum simulation requirement necessary. That way I can focus on what it is that I'm trying to accomplish with the minimum kinds of issues like convergence and the minimum simulation time. And simulation time is expensive. I talked a little bit about how it is that I use this unique hybrid approach to determine the time domain results from a frequency domain response measurement. And one of the reasons for that is that it simulates much, much faster. And the hybrid approach that I published with National Semiconductor, we simulated, I think it was about between 5 and 8 times faster than a standalone transient model. And now with it ported to ADS, that same time domain response runs almost 100 times faster than it would in a time domain simulation. And yet you can see here's the overlay of the ripple simulation and measurement, and they're nearly perfect. What are the imperfections? The imperfections are little glitches that you can see just before and just after the pulse. Those are before and after the dead time of the top and bottom switch, and those occur from the distributed capacitance across the MOSFETs through the printed circuit board. So it's not that I can't simulate those glitches. Of course I can. But for the purposes of measuring ripple, I don't really want that extra baggage, and I don't really want the extra simulation time. This was enough for me to validate the peak to peak ripple result. And so these results came from the same state space average model, which is really a behavioral equation model. But from that, we can also derive the time domain. And so the point again is that these can be extremely accurate. Next, we have test setup issues. So we tend to simulate and measure quite differently. In our simulations, we draw cables as lines, and a line is a wire that has no transmission line effects, and a wire has no resistance, and a wire has no inductance. It's a direct connection. In our measurements, it doesn't look like that. And so here I created a simple two-port impedance measurement. Here we have a ground isolator here, and we're measuring a little resistor here. And then, of course, we have these two short cables that go from the two ports to the VNA. And I measured that three different ways. One is without using a ground isolator at all. And you can see that that measurement's really odd, right? The right answer is down here. It's a flat 2 milliohm resistor. If we use the coaxial transformer, we get a better result, but way down here, it's still kind of wacky. And if we use a solid state isolator, well, then we get the right answer. And all of that lies in the shield resistance and coupling of these two cables, the common mode isolation from this transformer. And so if we want to match the measurement, we really need to include all of that in our simulation if we expect to get the same results between simulation and modeling. The same thing goes true when we measure capacitors. So I take a capacitor and I almost always mount them to a circuit board to get the most consistent results. And then I typically save the circuit board with the capacitor. I don't remove the capacitor. I bag and tag it, and I archive that in case I ever have to go back to it. But when I measure the capacitor with the printed circuit board mount, I get this upper trace, and the inductance is much higher than the capacitor itself. The downside to using that upper trace would be that we would use a lot more capacitors than if we use this lower inductance here. We could do that with much fewer capacitors. But that gets into the details of the simulator I'm using. So in a SPICE simulator, SPICE doesn't know about the inductance of the vias to the ground plane, whereas the EM simulator does. And that means that we need different models for the capacitor if we're going to simulate it in SPICE versus if we're going to simulate it in an EM simulator. In an EM simulator, we need to remove the excess inductance from the mounting vias. And in SPICE, we don't remove those vias, and ultimately they should end up at the same answer. And that'll tell us how many vias we need. And of course, there's yet other contributions to our measurement that don't occur in our simulation. That is, there's also noise in our measurement, and the noise doesn't show up in our simulations either. And so if you want to see the noise, you can. You just need to add it to the simulation. So while you may be simulating an ideal, perfect, beautiful sine wave, you might get something that looks a lot more like that. And if you want your simulation and your measurements to match, then you need to include that noise also. Frequently I make this measurement so that I do know what the noise is, because one of the things I'm always paying attention to is the signal noise ratio, and is the signal noise ratio of the measurement high enough. Some of you might have seen that we're doing an online measurement class, and in the online measurement class, this is a major focus of our attention, is where is this noise, how does it get there, how do we minimize it, and how do we account for it. A few years ago, I did a series on designing power for sensitive circuits, and I did this as a webinar, and there's also an article in Signal Integrity Journal if you're interested. But this is an oscillator that's mounted on one of our demo boards in particular. This is the VRTS3 demo board, and this is one of the oscillators on it. It's 125 megahertz reference clock, and we can power that from 3 different power supplies. There are 2 on the demo board. The green trace here is a little switching regulator that's on the demo board. And the linear regulator is this black trace here that's also on the demo board. And then we measured it using something approaching noise-free, and that's one of our injector products. And you can see we get very different phase noise. And if you look down here in the lower right-hand corner, you can see those are all also listed as jitter. And you see the jitter is really different. And so one of the things that engineers really need to learn is that most jitter is induced by the power supply. And if you were to look at this power supply, this is about 10 microvolts of noise down here and a little less than 1 millivolt of noise up here. One thing that's particularly interesting, and if you're interested, you can look up the webinar or the article. It's a 2.8 megahertz switcher, and you can see here's the spur right here at 2.8 megahertz. Spurs have almost no area. It's a very narrow frequency width, and so it doesn't generally contribute much to jitter. It's an annoyance, but it doesn't add much to jitter. All of the jitter is right here. And so one of the interesting things about this measurement is why would there be so much 30 kilohertz noise in a 2.8 megahertz switcher? And that normally wouldn't be modeled. So the whole series in designing power for sensitive circuits is about how it is that that noise got there, how we quantify it, and how do we design the ideal power supply that just meets the noise-free performance. We don't want to overfilter because it's too expensive. We don't want to underfilter because then we won't have a really good reference clock. And there is a way to get it exactly right using simulation and measurement together. And that's the basis of designing power for sensitive circuits. It really is fascinating, and I'll cut to the chase, is that most of this jitter that's coming from the switching power supply is coming from jitter in the switching frequency of the switching power supply. And I don't know whether it's intentional or non-intentional. Some power supplies do that intentionally to minimize EMI. And in this case, there's no mention of that. Generally, they would mention it because they charge more for it. So I think it's just a relatively poor oscillator, but that's where all of that noise comes from. And also you can see they all have the same frequency of peaking, and what that tells us is that's where the clock is really sensitive, is in that 30 kilohertz region, and that's probably about the bandwidth of the internal phase lock loop in the oscillator. There's other things that we got to be aware of, one of the things that you learn when you're doing worst case analysis and worst case analysis modeling and simulation is we really want to focus on the things that we can't see and what's wrong, whereas that's kind of counterproductive for engineers. Engineers really like to make things go fast. They want to show how good it is and how they did better than the next guy. And the art of worst case analysis and optimization is looking at it from exactly the other perspective. Where are the weaknesses and how do I improve them? And so that's one of the reasons that I often tell engineers that you shouldn't be doing the simulation and analysis of your own circuit, because you'll avoid finding those bad things where somebody independent won't. But this is an evaluation board I got from Texas Instrument for one of their digital power supplies, and I can tell it's a lot of years ago because I was using, looks like an MDO, I think it was an MDO 3000 in those days, so that's back probably around 2011. Anyway, they wanted to show me this impressive transient response they got from their digitally controlled power supply, and arguably that is quite beautiful, 4 millivolt excursions, and that measurement is at 2 milliseconds per division. Of course, I like to look at other places too, particularly when I'm measuring in time domain. I like to look at very wide spans and large voltages, and I like to look around because time domain doesn't really have a lot of dynamic range in either the X direction or the Y direction. So we really got to hunt for stuff, and it didn't take me long to find this picture at 1 second per division and 100 millivolts per division. And you can see here there are hundreds of millivolt transients every few hundred milliseconds or so. And these happen to coincide with where it is that the interrupts occur in the DSP that was controlling the power supply. So I got this little note on it that says you probably needed to disable the interrupts. And so we're looking to find those kinds of things too. And in simulation, that would mean that we needed to include all of those effects, including what happens to the timing when we get interrupts. I don't trust anybody, I don't trust anything, and so I'm kind of a pessimist, and maybe that just goes along with worst case analysis. I'm supposed to be a pessimist. It's a big part of my job. But here are two examples I wanted to highlight. This one on the left, this is actually the Ref 03, and it's a high reliability voltage reference for military and space designs. I think it's maybe about 16 years ago I first measured their evaluation board, and I told Analog Devices back then, around 16 years ago, that the application circuit, the recommended circuit, and to this day, their data sheet says they highly recommend 0.1 microfarad input and output ceramic caps. This is the step load response, and you can see the horrific ringing. You can also see something else if you pay careful attention, and that is that these two different current levels, these are only about a few hundred microamps apart, but you can see the responses are different. The circuit is really, really sensitive to operating current. That's not what I'm picking on, but it's a nice thing to note here. And so when we make these models, we need to make sure that we capture that too. And if we look at simulation, well, here's the output impedance of the reference without their recommended 0.1 microfarad cap. And here it is with the 0.1 microfarad cap. And of course, the peak is the cause of all this ringing. And it also shows up in noise density. So I'm not sure why you would want a noisy voltage reference, but that's what the reference circuit generates. I think it was about 6 or 8 years ago that we measured this again. In fact, we feature this part on our demo board so we can show it off and show how bad these reference designs are. But about 6 or 8 years ago, I wrote to Analog Devices again, telling them I could see that they improved their process because they used to have 8 degrees of phase margin, and now they only have about 5. So I don't know, maybe you could see that as better. I see that as worse. And similarly, I got this plot in a data sheet from Semtech. This is one of Semtech's voltage references. I took my own measurements about 9 years ago, and I checked the data sheet just before I made this presentation. It still says what it says. Here's their output impedance with no capacitor, and here's their output impedance with a 1 microfarad capacitor. And if you draw this capacitive line, it takes about 30 seconds or so to see that that's actually 3.2 microfarads. And so I called Semtech and I said, your data sheet's wrong, and it's not 1 microfarad, it's 3.3. And they thanked me for pointing it out. They said a 3.3 microfarad cap must have gotten in the bin. But to this day, 6 or 8 years later, it still says that that's the impedance with 1 microfarad, and it's not. It's the impedance with 3.3 microfarads. And so this is the reason that I only trust my own measurements. There are a few people that I trust now, but not many. Trust nobody, trust nothing. We have to start out with the presumption that the models are wrong, and we need to be proven otherwise. And we generally do that through data. So I said this earlier, and I'll say it again. One of the things that a worst case analyst is trained to look for is what's missing, what wasn't said. In the case of Space Station, I remember one design review that I was sitting in, and I noticed that they took load current data in 1 amp steps, except that a few were missing. They had 1, 2, 3, 5, 7, and I think it was 10, 11, and 12. And I asked what happened to all the other ones, and they said those were bad data, so they tossed them. And I said, so I want to go see those data conditions, and of course that's where the power supply wasn't stable. If you remember the O-rings in the space shuttle, the O-rings also happened because of omitted data. And so what we're looking for is accurate validation. We're looking for good documentation. We're looking to make sure that it included all the applicable tolerances, temperature effects. We want to make sure that it can do all of the things we needed to do, AC and transient. And we also need to make sure that it tracks different conditions. So like I said, the voltage reference and most linear regulators are highly sensitive to different load currents. And one of the ways that that shows up is that it has a changing inductance as a function of load current. There's 2 articles you might be interested in if you're interested in that topic. One of those is the inductive nature of voltage control loops. And I believe that that's published in Signal Integrity Journal. And there's also one called How to Stabilize Any Control Loop in 5 minutes or less. And that one also is in Signal Integrity Journal. But we're looking to make sure that the model isn't only accurate at one point, but that can track different things, like that it responds properly when you change the input voltage, and it responds properly if you change the load current and things like that. One of the things that's required for us to do that is we generally need to to make our own measurements, and I don't trust anything. In fact, at this point, I don't even trust most printed circuit boards. And so we generally make our own printed circuit board to characterize parts, and that way we could put monitoring connectors and test points where we want them. And it also means that we have a good, accurate layout for our EM simulations. And so very often we make our own boards for that. And I hear this from automotive companies very often. They say, how do we make fewer board spins? These board spins, they take forever and they're really expensive. And I said, it's simple. You just need to make more boards. And they say, well, that seems really counterintuitive. And it sounds it, but it's not. If you make more of these 2 and 4 layer characterization boards, by the time you get onto your 16 layer board, you'll know it's going to work. So you may have some of these very quick spin 2 and 4 layer boards, but it's going to save you 16 layer board spins. And so a big part of our measurement process is creating this evaluation printed circuit board. So what did we learn? We test for verification and correlation, and it's really an essential thing. Most of the time you're going to have to develop your own model. There are a couple of good books, including my own, on how it is that we do that. If you can't make your own model, you're really going to need to spend time validating the manufacturer's model, and I can tell you to be very frustrating because you'll go through the process, and most of the time what you're going to find is the model didn't accurately represent the part. We tend to like to do the output impedance first. It's a closed loop function, and if you didn't get the output impedance right, you won't get anything else right. It's also a very simple measurement, so that's typically where we start. A lot of the new regulators, we can't make Bode plots for measurement either, and so you need to go to other techniques like the PicoTest non-invasive stability measurement, which is available for most vector network analyzers today, and that's also impedance based, which means that we really need to make sure that the output impedance data is accurate, and so we usually start there. So takeaways are simulation and measurement, they go together, and it's kind of a cyclical thing. You're always locked in this loops, simulate, measure, model, test, simulate, measure, and we're either doing that to consistently optimize, to troubleshoot, to check components, to get small little models like a ferrite bead. We're always in this loop of measure, model, simulate, measure, and that's not necessarily a bad thing. In fact, when we started getting into decent modeling efforts around 1990s, early 1990s, a lot of the engineering bosses decided that since we have simulators, we don't actually need to build breadboards anymore. And I have to tell you, that was an absolute disaster. So we went back to building breadboards, but then the engineering bosses didn't understand why we were doing simulations. And I have to tell you, they go as a matched set. And what we're ultimately working on ourselves, my focus is always the accuracy of that model, knowing that at some point I need to rely on a simulation that I'm not going to be able to measure, and I want the confidence to know that when I do that, I'm going to get the right answers. And it takes a lot of effort to do that. Make sure you target the fidelity. I'm not saying that your model should be accurate for all things. In fact, I would probably tell you exactly the opposite. What I would tell you is that you need to simulate what really matters accurately. And so those things that you need to model accurately, you need to spend a lot of time on. You need to model a lot of detail. You need to compare it to a lot of measurements, and you need to make sure that it agrees over a wide range. If you don't get good validation between your measurement and your models, one or the other is not doing what you think it's doing, or both. Sometimes it's both. So you really do need to stay in the loop of measure, model, simulate until you end up with a measurement and a model that are in agreement with each other and over a range of operating conditions. Follow the modeling flow and you'll stay out of a lot of trouble. And like I said, when you jump, your simulator will catch you. And that's what we're hoping for. We're hoping the simulator is going to catch us. I hope you enjoyed the session. I want to thank you personally for attending it. If you're interested in more information about the measurements that we make for our models or modeling efforts, you can visit our measurement solution page. You can also visit our blog. We have a publications page, and if you sign on to that, you can also get our newsletter. Yeah, you'll find lots of things about modeling, and most of my articles are also on that blog. I'm on LinkedIn, so you can join my Power Integrity for Distributed Systems group. You can just connect with me on LinkedIn. You can message me on LinkedIn. You can write to us at info@picotest, or you can write to me directly at steve@picotest. I promise I don't mind. However it is that you get your questions answered, we want to make sure that they do get answered. And with that, I'm going to close this session, and hopefully we'll be able to go ahead and take some questions and answers and see what you guys are interested in knowing. Hope you enjoyed the session.
Steve, it's nice to see you again. But no, can you say something? I just want to make sure that we got full audio connection here, Steve. Oh, I think we might.
There you go.
There we go. Perfect. All right. Excellent. It's a pleasure to see you again, Steve. I'll be thinking about you tonight as I make your pizza dough, because as you told me, I never knew. I do a 2-hour rise, and apparently it's got to be 3 full day rise. So I'll be looking forward to that. I also bought the flour that you recommended, so I'm not kidding. So we did.
Tell me how it worked out.
I will. You know I will. So I also think we did get a good number of questions, and I'll get to this. But I have a question. First question: I need you to stand up, go to your bookshelf, and pull out your favorite book. I'm kidding. It's an impressive bookshelf that you have there, Steve.
Thanks. I have got requests to take pictures of it so they can see what it is that's in the sweet spot of my real estate on that shelf.
Right. Yeah. Which books are you featuring exactly?
Exactly.
So in any case, the first question I have actually is a question that it's actually from the previous session that we didn't get to from the panel that you participated in, Steve. But I want to bring it up because I think it's a good question for the audience that we typically have at these events. Because it's hardware engineers, and simulation can sometimes and it can be like an exotic thing, and it's not fully mainstream yet. But who's responsible for validating these models? That comes up. We see this sort of rivalry quite a bit.
That's a great question. And the answer, unfortunately, is generally nobody.
Yeah.
That's part of why it is that we end up in so much trouble. A lot of the semiconductor companies, they use interns to make many of their models. And the entire simulation ecosystem in these simulator companies is actually part of marketing. It's not part of engineering. And so, for them, it's about, do these models make money? Because if the model doesn't make money, we're not interested. And so many of them just view it as kind of a checkbox. If we say we have a SPICE model, we'll be able to sell more parts. And so we'll have a SPICE model. We just won't necessarily say it's so good. So who is responsible? At the end of the day, the guy that's doing the simulation is responsible to make sure that the model that he's using is valid. And most of the time it won't be.
Most of the time it won't be.
Right.
Wow. Well, I had no idea. That's actually quite interesting that marketing is actually responsible for the models. It kind of makes sense. I would say it's a content exercise, really, if you think about it.
Exactly. Yeah,
Wow.
Exactly. But so they're not overly concerned about the accuracy of them. They're much more interested in just being able to say they have one.
Wow, well, that's great information. I guess buyer beware. That's great information, Steve.
Yeah, exactly.
So this is one that came up, and I also have been wondering this myself, because I know when I listened to your podcast that we did with you some weeks back, we talk about the space station. And obviously, as I've said now, I think more than a few times through the course of this just 2-day event so far, big fan of space, love space stations, spaceships, all things NASA, space, and the like. But when you talk about simulating the space station, do you mean are you validating the interfaces between the subsystems from a signal integrity perspective, or is it more comprehensive than that? I guess people want to get a little more depth there.
Well, that's another really great question. So, personally, I was responsible for the space station power system. And so that is the solar arrays at one end, and solar power goes to the battery charger discharger unit, and the charger discharger unit either uses it to charge the batteries or to discharge the batteries to power the bus. And of course, there's many electronic circuit breakers that are in the way, and fault isolators, and DC to DC converters. So my responsibility was that entire power train that included the solar power all the way to the end. Now, one thing that's really fascinating about the space station, most people probably don't know this, is that most satellites have separate battery charger and battery discharger units. And so when you're in sunlight, you're charging the batteries and using the battery charger. When you're not, then you're discharging the batteries through a separate discharger unit. And in the space station, in order to save weight, two brilliant engineers got together and said, you know what, we can only be charging or discharging at one time. And so we could save a lot of weight and maybe a lot of cost if we made a single bidirectional unit that could both charge and discharge. And that's called the bilateral charge unit, BCDU. That's the charger discharger unit. And it's probably the most sophisticated piece of electronics I've ever worked on. Just the printed circuit board for the pulse width modulator in that charger discharger unit has 14,000 components on it, just to do the pulse width modulation of the battery charger discharger unit. And I love stories, so let me tell you one more really quick story about that charger discharger unit. It was the brainchild of two really bright guys, one at Rocketdyne, who was the prime contractor, and one that was at Space Systems L'Oreal, and they were the major subcontractor. Within 6 weeks, both of those guys died. One had a brain aneurysm in his office, and he died, and one fell off a cliff rock climbing. There were no notes. Now I knew why it is that our professors were so adamant about keeping really good lab notebooks about everything we did. It took us 3 years to figure out what these guys knew and reconstruct it. Crazy story.
Well,
that's true.
Well, that leads me to a question, not the morbid part of your story, but on the discharge. What's the battery chemistry that they're using?
I don't know if it's the same as it used to be. Now I believe it's lithium.
Lithium.
They used to be silver.
So now when you talk about charge discharger, now when they're in darkness, are they discharging, are they trying to fully discharge through that cycle for some?
So, well, remember that the space station is circling around 18,000 miles an hour, right? 17,600 miles an hour, give or take. Sure. And so about every 90 minutes, it goes through a solar eclipse. So while it's in the sunlight, you're charging the battery, and when it gets out of sunlight, you're discharging the battery. The goal is never to discharge the battery fully. The goal is never to lose the power bus.
Well, my question is, I guess, is from a battery health perspective, really.
Yeah.
So in other words, partial discharge then recharge. I guess that's the reason there's 14,000 components in that unit potentially.
Yeah. In fact, I don't know anything about any health monitoring for the batteries in the space station. You know, a lot of people do monitor their batteries. In fact, I'm working with some of the cloud companies now on battery state of health. And usually we use impedance measurements to do that. It's impedance spectrography. And we can tell about where it is that the battery is in its life cycle based on its impedance data. We didn't have anything sophisticated like that in the space station, at least not that I know of.
Interesting. Okay, so now this question, I think, segues quite nicely with the question about models, which I liked that question as well, Steve, and I'm glad you answered it. And I was shocked by your response, quite frankly. As the marketing guy, you don't want me nowhere near supplying models for you guys. This question here is, I understand the first step to have an accurate simulation is to have a good device model. Well, clearly we've established that that's probably out the window. But what about the effects caused by the imperfect connections on my board layout? How is it possible to assess how my board layout would disrupt the behavior I got from the perfect connections schematic? There are tools that integrate my board layout to the SPICE simulation. Does that did you get that, Steve?
I did, actually. It's a really good question, and I talk about that sometimes. In fact, in our online classes, I have a class about it. In particular, when we make two-port shunt-through impedance measurements, the staple measurement of power integrity, one of the things that's in the way is the resistance of the shield in our cables. And in fact, that's the reason that I designed our own coaxial cables at Picotest. It's because we needed a cable that was really thin and flexible, but also had much lower shield resistance than typical cables. And so what I tell engineers is it's really important that you understand those connections and that they do need to all be included. And that's true not only of coaxial cables, it's also true with connectors. The DesignCon session I did with Heidi Barnes and Jack Carroll at Xilinx back in 2018 actually turned out to focus on the impedance of a connector that was the cause of their issues. And so again, those need to be included. And so now there's a really short leap to figure out how it is that I became a Keysight ADS certified expert. And that's because that is capable of doing the cables and the printed circuit board and the analog stuff and the digital stuff all in one simulation environment so that you get an entire holistic simulation.
Mm. All right, well, so just looking at the clock here, this will be the last question, Steve. And so this one, I actually, as I said earlier in a session, I talk about a lot of people ask where the young people are in our industry. And clearly based upon the social media posts, a lot of them are here, which is really excellent. And by the way, we have seen in the live events that the age does seem to be coming down. We do see younger people now getting more interested in our field, which I think is really excellent because I find it to be quite exciting, obviously. But my question here, someone else had it, which is, now as the tools have gotten better, I think the abstraction from the sort of physics of it gets greater. And so the question is, how does a young engineer really get started here in modeling? And do you see an appetite amongst the younger engineers coming into the industry?
What I'll tell you is I love working with the young people because they're our future. And I really like the hungry ones, and I like the ones that are willing to do a lot of work on their own. I don't really like the ones that call and just ask me if I can give them the answer. Now, what I'll tell you is that it's a long process to learn how to do modeling. It's not really straightforward, and it's not part for part. The best things that you can do are to try to study existing models, learn from them, do a lot of simulation. And if you know somebody that knows how to model really well, an apprenticeship goes a really long way. And so if you can get somebody that'll mentor you through that process, that'll be great. You can't make good models and you can't validate good models unless you're really good at measurement. And so I'd say that's the second thing is you have to be really good at measurement in order to either assess them or to create them, whichever direction you want to go. So those would be my keywords of wisdom to younger engineers. But I would tell you that there's tremendous value in having these skills. And so it would be a wise investment in yourself.
I think that's excellent advice. I also just would add to that, I think this goes back to, what you said, you're talking about a mentor. I think our industry, for a large part, has been built on that apprentice and mentor relationship. And I would encourage and I think this came up in the panel discussion as well, some of the older folks to really get sort of deeply enthusiastic about being mentors. Because passing this information down is absolutely one of the things that we're trying to achieve here with our AltiumLive series. And so with that, Steve, not to insinuate that you're getting old, but certainly appreciate the mentorship that you've provided in all your discussions this week. So thank you so much. Again, I appreciate it very much, Steve.
Well, thanks for having me. And I don't think getting old personally, it beats the alternative.
Well, neither do I. Thanks.